This week begins with what measurement is and how we're going to view it in relation to risk. Last week we talked about what risk was, what safety was, and we got a good overview of it. The first chapter is relatively short. The second chapter is also short, but there's a lot of information in it that helps us understand how risk is measured and what it means. So this week we'll be covering more of the scientific data. There will be minimal mathematical equations that we will have to do that you'll need to learn to understand a couple more of the concepts in the next lecture, but it's very basic, non-calculator, easy stuff to do in your head, just so you grasp the concept, not how well you can add and subtract. So we'll start with measurement. So what is it? In simplest terms, measurement establishes a unit of measure or a scale, and it calculates ratios using the scale. For those that you can read a map or have seen a map, at the bottom of the map there's always a scale, and that scale converts generally inches and centimeters to miles. So if you're going 3 inches on a map, you would take it down to the conversion scale at the bottom, and it would give you a rough estimate of how many miles. In measurement, there's actually two systems. There's standard metric, which is worldwide. Um, for those that don't know, that's your millimeters. So the easiest example I think to give is a socket set. Your 9 and 11 and 13 millimeters. That's a standard metric set. Then there's the imperial system. There are 3 countries that use it. That's the U.S., Liberia, and Myanmar. Um, I believe Liberia and Myanmar are actually moving away from the imperial system to where the United States is going to be about the only one that continues to measure things using the imperial system. The imperial system is inches. Uh, so your quarter-inch sockets, your half-inch sockets, 5/8. That's what we're talking about when we say imperial. However, for those that you have traveled, you'll notice that a lot of countries have both measurements. They have both the standard metric and the imperial system on signs, especially on freeways and highways, giving distances. So let's take a look at this here. This is a Sharpie. How big do you think it is? Well, let's go ahead and take a measurement of it. As you can see, there's 2 different scales here. Uh, on the imperial scale, you'll see that it's a 5 1/4 inches, and on the standard metric, you'll see it's roughly 13 1/2, 14 centimeters. So when you look at that and you're reading something, and maybe it's a study that's measuring something in a different type of measurement that you've never heard of, it is important to know that scale, because all of these are the same measurement, but they're of that Sharpie, but they're all in different sizes and different types of measurements. And how you measure something and then how you relay that data to someone can actually affect how they think about it. So for us, 5 1/4 inches, you would see, you could picture that in your mind, and you could say, okay, I could say it's about an inch less than a dollar bill. For those that you don't know, all our money currency in America is 6 inches. So if you ever need to know what 6 inches look like, you can always pull out a bill. But a 5 1/4 inches for Americans or somebody that grew up on the imperial system, you can quickly think and say, okay, I know what that means. But if I said 135 millimeters, now in your head you've got to convert um, millimeters to centimeters, and then you have to understand what centimeters to inches are for you to truly grasp the concept. Um, Normal people to grasp the concept of what millimeters are. And then if I was reading a study and it was 135,000 microns. Well, what's a micron? How big is that? If it's just taking out of context and somebody says, wow, that's 135,000 micron. But if I'm not absolutely sure, or it's just some part of a study that I don't know anything about, what we're really measuring, to me that might sound big. Wow, that's huge. When in reality, it's 5¼ inches. Now that we've talked about what measurement is, let's talk about scale. The scale of measurement has to do with how the measurement is being looked at over a time, distance. Generally, it's time when you think about scale or size. So we talk about the chaos theory, and you look at these two lines here. The top one is the 95% confidence bound of this study, and the bottom one is the actual temperature increase over a 10-year period from 2001 to 2011. So our measurement is temperature, and our scale is 10 years. And as you look at it, you don't really see. You can see that there's peaks and there's valleys over the 10 years of the increase and decrease of temperature, but is it really telling you anything? So the chaos theory is when you observe results at one scale, it might appear to be chaos. Like the previous screen, it's not really telling us anything, and there's no trend in it. You look at the same results on a different scale. Take example of the picture of the hurricane or tropical storm in on the screen. As you look at that, you see the scale is much bigger. You're seeing it from the satellite image. You can see how big it is. This is Hurricane Lane, but you can see here's the islands of Hawaii. So as a consumer of this information on a television, you would be able to compare and say, well, Hawaii is an island, and this storm is 4 or 5 times the size of it. On the other hand, if you lived in Hawaii right here on this island, you'd be seeing the storm out your window, and you'd be seeing maybe light rain. You could see the clouds maybe rolling in, but you're not seeing the same scale that somebody is looking from the satellite. So we move back to our weather, and we'll talk about scale some more here and changing it. So they've now expanded this scale from 1975 to is what we're going to look at all the way to or I'm sorry, 1970 to 2010. So expand the scale from 10 to 40 years. And now that you look at it, you can see that there is a general increase over the 40 years in these temperatures. Um, so somebody has gone and added a trend line every 10 years just to show the change in temperature over 10 years. But as you can see, there is a general increase over 40 years. And now that's a little bit more easier to see that you have the 40 years of data. Now, how do people use this? So, if you are a contrarian or you don't necessarily believe in global warming, you would use the 10-year scale, because adding a trend line, even though it's over 40 years, and 40 years you can see there is a increase, by adding these trend lines every 10 years, you can make the logical argument that over the 10 years there's been no significant increase in temperature. From 1980 to 1990, there's no significant increase in temperature. Uh, and so that's one way to use this. Realists that believe in global warming or that it is a potential problem would use the scale differently. They would add one trend line over the 40 years. This trend line definitely shows that there is has been a gradual increase of temperature, and it seems to be ongoing. So again, your frame of reference, changing the scale. Some more examples. The SAT in '95 had to recenter what the actual national average was. because math and verbal scores had been steadily going down. So was it that we were getting dumber as a country, or was the majority just the average shifted? So they shifted it in 1995. Same thing with AP exams. They eliminated penalties for guessing. So for those that are unfamiliar with this process, um, if you have 25 questions and you know 20 of them and got those 20 right, you would get 20 out of 25. But the way AP exams would do it, you actually penalized for educated guesses. So if you missed those 5 questions and you guessed a wrong answer, you actually penalized for a wrong answer. So there's some algorithm that they use, and it would actually reduce your score from a 20 out of 25 to lower. Um, because of that, we had an increase of failure rate of almost 40%. So we were telling basically what we were telling young students was that your guesses are worse than you just not even answering. So they eliminated those penalties. So now it encourages somebody to make a guess, an educated guess on an answer, than just leaving it blank. And then the consumer price index. Many government payments are tied to the consumer price index. By just changing the definition of what the consumer price index was, we saved almost $1 trillion in 10 years. So the practical laws of measurement are outlined in your book. There are 6 of them, and we will cover them. So law 1, practically anything can be measured. This is absolutely true. Technology keeps advancing. We are able to measure the smallest of atoms. Um, we measure how people feel. We measure how people think. We can measure brainwave activity by showing people images and reading their brain waves and how they react, and then making an assumption based on that. So how do we use them? How do we use these measurements? Is what is important. We say that there's an overwhelming amount of information, and there really is. For any of you that have done any type of scientific research, you can get lost in the data. There are so many studies, especially if you do something that's you're building on a study that's already out there. You're using a topic that's popular. Um, they the amount of data that you would collect, and then you have to sort through it. It can be overwhelming. So when we say practically anything can be measured, it's absolutely true. And you need to understand, how are we using the measurements we're taking, and then how do they affect us in our decision making skills, especially when it comes to risk. Our second law is tied to the first one. Just because you can measure doesn't mean you should, and this is absolutely true. The slide talks about the Ig Nobel Prizes. These are the absolute opposite of Nobel Prizes, and they're actually given out for studies and measurements that should not be reproduced. There are ideas that should not be measured because they're just silly. They're realistically wasteful. Um, Measuring an example is measuring how long shrimp can run on a treadmill. The United States government paid for this. We paid about $3 million for this study to see how long shrimp could run on a treadmill. The author and the scientists were talking about the study of a bacteria that was in water, tied it to water pollution, and basically said the longer shrimp can run, the better water quality we had. But in the end, it didn't. Uh, there was no correlation between them, or and and I say we because taxpayers paid for this. We paid $3 million to measure how long shrimp could run on a treadmill. You can do a simple search and find out how much wasteful scientific monies are used in the United States. There are lots of studies across the world that would blow your mind that somebody actually said that's a legitimate thing to study, and then somebody on top of that gave a bunch of money to study it. So when we think of measurements and doing scientific research, you should always think and say, is this a relevant study? Is it Are the results going to tie to what I want them to tie to, um, or is it just a waste of time? And if you can identify something pretty quickly, whether it's going to fit in um, to what you're trying to identify with risks and everything like that. So our third law: every measurement process contains error. This is very, very true. So, small errors can be significant with complex calculations. And we'll get into the example here of the Jet Propulsion Laboratory because I think it's very fascinating. Um, how very small calculations could have made a huge impact. But for those that you have ever done carpentry or worked with wood, they always say measure twice and cut once. Um, because if you a lot of people that don't work with wood a lot, they will forget to take the width of the blade that you're using to cut the wood in up in uh, into the account of the measurement. You're actually, when you cut something, you're removing, a quarter inch or an eighth of an inch of wood from the material, and that's from the blade. So a lot of people will measure and they'll forget that, and then when they cut and then they remeasure after they've cut, they're a blade length short. Um, the example here talks about this 2008 asteroid calculations. There was a gentleman that was looking up in the sky and found a celestial body, called it into the appropriate people, and within 20 hours of this discovery, it was it was projected that this asteroid was going to impact the Earth. Um, there are 26 stations across the globe that were tracking this thing, um, and the way it's supposed to be is that all of the stations would be on the same time, the atomic clock, but they were off. So to minimize the error of these time-stamped projections, the Jet Propulsion Laboratory took sample observations from all of the places, re- reducing the amount of error if they would have just taken or observations from one single place, and then they selected all this data and used it, compiled it together, and it reduced the total amount of data that they had, making it easier to understand and process. It also reduced the amount of errors, and it made for a better and more accurate prediction. And so the prediction was that it was going to strike the Nubian desert in Sudan, and they were off very little by time. I think they were off by 15 seconds overall time wise. And then uh, measurement distance wise, it was very little um, off the exact predicted spot. So that was a error of time stamping because all these centers were off. But there are other errors, and a lot of it has to do with predictions. So we move on to Law 4 here. Every measurement carries the potential to change the system. And this is the Heisenberg principles in physics, if some of you will remember. You measure position of a subatomic particle and you affect its momentum. Effectively, what this says is you cannot measure the momentum and location of something at the same time. To measure the location of something, it needs to be stopped. And to measure a momentum of something, it needs to be moving. The bicycle tire example here is a great one. You want to measure the pressure, but in order to measure the pressure, you have to reduce the pressure as you push a um, tire gauge onto the tire. It's going to release air. It may be minute, but it is a release of the pressure. A couple examples here. These are in your textbook also, but I like to cover them because I think they're really good examples. So in a call center, your employee will measure the speed of call and the quality of the call results. So if you're trying to make sales over the phone, speed and number of calls uh, are going, or number of sales are going to be what you're measured on, and potentially you're paid by on commission. So if you're on commission by the number of sales you make, then you're going to take the time, you're going to talk to people, you're going to give quality phone calls. However, on the flip side, which is also the same driver with a truck driver, if instead of being measured by the number of sales, you're just measured by your call volume, you may not have that best quality of phone call, because you can, once somebody says no, even if the training says, oh, well, get them to say no 3 times. Keep pushing somebody until they say no a third time. Well, if they say no one time and you're being paid by the volume, you're gonna want to push through that call to get to another one. The same can be said for over the road truck driving. If you're paid hourly or salaried, um, you're going to get paid no matter what. Vice, if you're paid by the mile, a truck driver is gonna want to put as many miles as he can um, in order to achieve the best paycheck. So when you look at um, how the workers are being measured, this really applies to safety, especially with fleet management. Is if you're telling a driver that we are going to pay you by mile, they're going to want to put in as many miles as they can. You're going to increase the rate of speeding tickets or potentially for accidents in the paid by the mile drivers. You're going to increase the fatigue of the drivers. You're going to potentially increase the stress, which all could lead to workplace injuries. On the other hand, if you're paying drivers by the hour and you say you can't drive any more than 12 hours a day, that driver knows even if I don't make it from point A to point B today, I'm still getting a paycheck, um, because I'm only expected to go 65 miles an hour, potentially 70. Depends on which interstate they're on. And I'm being paid only 12 hours a day. So an employer is saying, we value your safety, we value your time, and we want you to be on the roads, we want you to drive safely, we don't want you to push yourself. Uh, in turn, it reduces the likelihood if you have a traffic accident or driver fatigue, and it reduces your injury rates. Law 5. The human is an integral part of measurement. The Hawthorne effect, there's these 2 examples. The first one's the Hawthorne effect. The Hawthorne effect it's also in your textbook for more information on it. But what it simply was is a workplace measured um, if they provided better lighting, did more production get done. So what they being the employer, wanted to look at is if they provided better lighting, would it increase productivity? It did. It did. The study did show that if you gave workers better lighting, they would work. They would be more productive. When the employees were then asked about it, they said, "Well, we worked harder because we felt we were in a better place." So it wasn't necessarily uh, the lighting was making them more productive. It was the lighting was increasing the how they felt in their environment, that they felt safer in their environment, that they felt that the employer cared about them. That's what the workers showed as an increase in their productivity, where the research just showed if we increase the light, workers will be more productive. But the workers were saying it was more of a feeling for them, that now they had better lighting, the employer cared for them, they wanted to work harder. The early days of AIDS testing, um, the way this is this was done in the 1950s, mid 50s, I believe, um, is they thought that if they tested more people um, to see if they had HIV, the more that they would test, that they would increase uh, the acts of unprotected sex. What the study was saying is that if 100 people came in and said they were negative and they had been continuing unprotected sex, they would say, well, my test was negative, I'm not doing anything wrong, and it would not increase their sexual awareness. Again, uh, the conclusion was to not test people. That way, people didn't know if they had it or not, or their partners didn't know if they had contracted HIV or not. And the idea was that people would have more protected sex because of the unknown worry about HIV. Law number 6, you are what you measure. What the CO is measured on affects the corporate behavior. So a CEO is generally measured on profits and losses. So if you think of um, $1 billion industry, and you're a factory that is producing $1 billion a year, or a company that's producing $1 billion a year, and then the next year you only produce 800 million. Well, you've taken a loss of 200 million. Your stockholders and your shareholders don't necessarily care why that loss is there, but that's what the CEO is measured on. So, um, one of the things that we want to talk about this is the airline performance, and how it has is a good example of it. So they recentered their own departure, their own definitions of what a departure time was, when it was, um, and what happened is schedules changed. They got longer flying time, and the question was, well, have planes gotten slower? And we should all know that no, they didn't. But what it was is they changed their definition of when the departure time was. So, for all that you have flown before, you understand you've got to be at a gate X amount of minutes before that flight to board it, and generally it's 10 minutes before the flight is going to take off is last call for boarding. So the definition change was from the departure went from when the plane actually left the ground to when the doors shut at the terminal. So if you look at the increase um, in this little chart here, you actually decreased, and then you increased another 15 minutes. So the way they look at it is they're saying um, the time it takes from those doors shut to getting off is a 10 or 15-minute span, but there's an electronic log on most airplanes that um, will send an electronic signal from the plane to the departing terminal and the arriving terminal, and that determines when it left and when it actually landed. There were a few airlines in the past that didn't have this technology yet, and so there was a error in their reporting based on when the pilot himself was calling in, they departed, and calling when they landed. So you can see how um, airlines could get, where we see with this American Airlines, it's 5 hours and 40 minutes. But if the Southwest, for example, didn't have the technology and they looked into their last year of flights and calculated, well, to get from Miami to LAX, it only took us 5 hours and 30 minutes, it could skew how a customer, me and you, would look at it, and we'd want to buy the shortest flight. And then it would also say, well, how is Southwest 15 minutes or 10 minutes shorter in the same distance? So you have to be careful on what your definition uh, of something is that's being measured, because how you define it becomes who you are. And this is a very important and important role pertaining to safety. So as injury rates and measures and metrics are measured and compared across industries and across companies, you need to it's important to understand the root cause. Um, a company such as John Deere has many different factories, and to be able to compare injury rates across, a flat. Say, I want all your injury rates for the last 10 years, and you would say, oh, well, factory A, you have the highest. You must be doing something wrong. In safety, you can't just say that, because what if factory B, who has the lowest, is nothing but in an administrative building? They do nothing but um, they have administrative assistants or marketplace analysts. They have lots of desk jobs, where factory A is actually out there building tractors. Well, of course, in that environment, your injuries are going to be much higher, where they're moving heavy metal around and they're attaching things to each other, and there's saws and there's presses, where in factory B, it's an office setting. There's no saws being used. People are coming working an 8 to 5 job. Uh, so when you get into the safety world, you have to look at what's being measured and how it's being measured and what's being defined for that measurement, because you can get into this comparative analysis and say, well, X doesn't equal Y. Why is this happening? Why is X better? And uh, it it sometimes is starting to get lost in the metrics and the measurements nowadays. So another thing we want to talk about measurements is the placebo effect. Most of you have understand what a placebo is. Um, it's a drug treatment or therapy that's generally used within control groups. So if you have a double-blind study, the control group is still going to get a pill. Everybody's got to think they're getting something. But with placebos, you will see a 20% increase of improvement within patients. And a lot of that is mental, or potentially the people didn't have um, as egregious of an illness as some others. But the power of positivity truly works, especially within medicine. So placebo patients will think they're getting better, and that thinking will make them feel better, when in actuality it may not be. It shouldn't be doing anything to an illness, or especially like a long-term disease such as cancer. It's not actually doing anything to the cancer, but it's more of a psychosomatic effect to them, and they're saying, I'm getting a pill. This pill is supposed to be helping me. Because it's supposed to be helping me, I should feel this way, and they actually do feel that way. So that's the placebo effect. You'll see that in a lot of medical trials. So this week, just to recap it, we covered measurements, the 6 laws. The 6 laws would be important. You should remember them, not by definition, but you should just remember what they are and the gist of how they are. Um, we need to read Chapter 2 and Chapter 3. When you read Chapter 3, stop at scientific studies. We'll get into those next week, so you don't need to read all the way through Chapter 3. However, the rest of Chapter 3 and Chapter 4 will be next week, so if you just want to finish up the chapter, go ahead. This week, on Wednesday or Thursday, I will release the first quiz. It will be over key points from chapters 1 and 2. There will be a little bit of math on there. That math will come from the second lecture. Again, nothing that you need to stress over. It should be relatively easy. It will be a timed quiz, but there will be ample time for you to finish it. The majority of the questions will be multiple choice, true, false, and fill in the blank. And there will be a math portion, a very small math portion, and then potentially a short answer. And then the assignment. This week's assignment is on the Triangle Shirtwaist Factory. It should be open. And you just got to watch a video and learn about that important event in the history of the safety profession.